Hi, I'm Mary, and I'm going to be showing you how to derive the equation for the angle of twist in a cylinder. So I've drawn our cylinder up here. It has radius RO, length LO, and a torque T is applied to it. I've also drawn in a plane with the dashed lines that shows a plane in the member before the torque is applied to it and before the member starts to twist. So this pink line here is the top of the plane after the torque is applied, and you can see that it's shifted from the original plane by an angle of alpha, which is our angle of twist, and also on the top by gamma, which is the shear strain. So now we're going to look at a small segment of the cylinder. So this segment has width dx, and I've also drawn in the two planes from above and a gamma as well. So this d alpha here is basically how much this little circular section twists when the torque is applied. And this rho here is the distance you go from the center of the circle. And when rho equals RO, you're at the circumference. So gamma is equivalent to rho times dA dx. So when rho equals 0, gamma equals 0. And when rho equals RO, gamma equals the max. So from this information, we can tell that gamma equals rho over RO times gamma max. So stress is linearly proportional to strain, so therefore stress is at a max on the circumference of the circle. And from this information, we can set up a similar equation to the gamma one with tau, which represents shear stress, equal to rho over RO times tau max. So now we're going to look at the force applied from the torque. So we're going to take a small amount of force from the torque, dF, and that's equivalent to tau times dA, an area element on the circle. So the moment arm of this force, because remember, a torque has a force and a moment arm, the moment arm is rho, and we can put this together to get an incremental torque, dt equals rho tau dA. So now if we integrate this equation, we get torque is equal to the integral over A of rho tau dA. And then if we plug in the equation for tau from before, you can plug in that 0 shouldn't be there. So it's just rho over RO T max times rho dA. And then you can pull out the tau max over RO because that's a constant, and you're left with rho squared dA in the integrand. So now a new piece of information we're going to use is the polar moment of inertia, which is J, and that's equal to this expression right here, which was in our torque integrand before. So now we can replace that integral with J, and we get torque is equal to tau max over RO times J. So we can simplify this. Tau max equals T times RO over J. And then if we don't want to deal with just the maximum situation, we can simplify it down to tau equals torque times rho over J. So now we're going to use the fact that gamma equals rho times d alpha over dx, and we're going to rearrange that to get d alpha isolated. So d alpha is equal to gamma over rho times dx, and we're going to use this other piece of information that gamma equals tau over g. So now if we plug that in, you get d alpha equals tau over rho g times dx, and then we can plug in the value of tau, which we found here, and you get this expression, and if you simplify it, you get d alpha is equal to T over Gj times dx. So now we're getting to our last steps. We integrate d alpha to get alpha, and alpha is equal to the integral from 0 to L, so over the length of our cylinder, of T over Gj dx, which is equal to TL Gj. So now in a cylinder, J is equal to pi r to the fourth over 2. So in our cylinder, we have to remember that L is equal to LO and the radius is RO. So if we plug in this information, you get alpha is equal to T times LO over g times pi RO to the fourth over 2. And if you rearrange the variables, you get 2 times T LO over pi RO to the fourth g. And there you go, you proved it.